Technical issues. Okay, welcome everybody to this talk about data parallel path tracing with object hierarchies, which is joint work together with Steve Parker. So in this talk, I'll be talking about interactive data parallel and GPU enabled path tracing for Moana-like content. So what we're particularly interested in is models that are larger than any one GPU, in particular models like Moana. So production content with lots of instances, with lots of shading data and so on. And in particular also for full path tracing, so not sideways like rendering, but real full honest to God path tracing. So if you read the paper is actually online on arXiv already. If you read the paper, there's actually three different things that this paper talks about. The first one is a new paradigm regarding how to think about partitioning data in a distributed rendering content, like which node can have which data. In particular, we want to enable nodes to have content in a way that different nodes can overlap, that we can replicate certain things, that we can split them up, etc., in a much more general way than is possible with spatial partitioning, which everybody uses today. So that is the main important thing. Then the second thing it talks about is some algorithms that realize this kind of paradigm. And finally, you couldn't actually evaluate that without having a complete system that is using that with the wavefront path trace and MPI and all that kind of stuff. So there's a lot of stuff in the paper. I could easily talk an hour about each one of those, but with respect to time, I'm only talking about the first 1.5 of those, and even those only in a motivational session, because if I can't convince you that this entire concept makes sense, then the rest doesn't even make sense. So data parallel rendering. The concept of data parallel rendering is that you have multiple nodes that work together to render a certain image and a certain model. So every node only has a certain part of the model, usually because the model is too big to fit on one, so you want to split it up over multiple nodes. A node might mean a GPU, it might be a physical node in the cloud or something like that. The way you do that today, most of the time, is via sort last image compositing. That is a widely used technique in scientific visualization. It works great, it's fast and everything. The problem is that doesn't easily work for secondary rays. So for ray tracing and path tracing, it's not so useful, so that's not for us. So the alternative to that, if you want to be able to trace arbitrary rays or path or whatever you want to call it, and a ray on a certain node is being traced and needs content that is on a remote node, well, you have two options. You can either fetch the model data, BBH data, and whatever else it needs from the other node and then do it locally, or you take this ray and send it or forward it to the other node that has the data. That's basically the two choices that you have. And there's a lot of discussion in the paper of why we choose one over the other. I don't want to go into that here. Just saying for this particular paper, we're interested in the forwarding approach. So rays travel across different nodes until they find the hit point and shade where that data actually is. So in that context, in the ray forwarding context, there's two questions that you need to answer if you want to do it. The first one is, how do you want to partition the scene? Like, which node gets which parts of the model? And the second one is, if I have done this partitioning, how is a ray being traced across these nodes? Like, what nodes should a certain ray be sent to? Which is the next node that every time a ray has to be forwarded? Where is it being forwarded to? And there's actually two interesting observations if you start looking at that problem. The first one is there's not much work on that. There was a lot of that in the very early times when dinosaurs roamed the earth. But in the last 2 decades, we've pretty much talked about that on and off in forums like HPG, but there's not much work on it. The second observation is that pretty much every of the recent papers on data parallel rendering assumes spatial partitioning. And that has some issues, which I'll talk about. But let me first talk what I actually mean with spatial partitioning. Take this kind of scene, and you have a few instances of 3 different kinds of trees or palms, whatever, and a few other objects. And now you want to do some partitioning of that. You could do a spatial partitioning like this grid, could also be a KD tree, OCT tree, doesn't matter. The outcome of that is different regions, which we call domains, that do not overlap. And each node, each rank gets one of these domains and all the geometry that overlaps that domain. That's a very, very simple thing to do. That's probably why everybody has done it. Now, if it's a spatial partitioning, that means that any object that overlaps multiple different domains, it actually has to be replicated in there. That's just the nature of spatial partitionings. We all know that. But again, that's easy. Also, if you want to trace array through that, it's easy. It's always very obvious which cells of this, which domains array has to traverse and which the next one is, and once it's done. So all of that is very easy, which is probably why everybody is using it. The caveat with that is that there's a lot of issues with spatial partitionings, which this community here over the last 1 or 2 decades has discussed. The community has mostly gone over to BBH style partitioning, object space partitioning for ray tracing. And there's a lot of issues that I don't want to go into. For our particular problem, the main issue is replication. So to explain what the issue actually is, let's have a look at the content that we actually want to render. So this here is a view, a top view of Moana on the top right. The full scene is actually larger because the ocean and the ocean floor are actually much larger than that. The white area is the beach that you see as the main shot cam, the main view that you want. That's where most of the instances for the trees and bushes and so on are. And if you zoom in on the beach, that's where you see all of the tiny instances where there's literally millions of those little twigs and pebbles and all over the place. So with that in mind, there's a few things I would like to point out for that kind of content. The first one is there's some meshes that span almost the entire model, like the ocean floor or the ocean surface or the beach or the mountain base meshes. They are gigantic compared to some of the instances. The other thing is that many of the things that have instances, they have instances scattered all over the model. Like there's certain trees that are on the left side of the island and the right island, and they're all over the place. And then in addition, in a rendering context, you typically do not want to split certain things, or it's not easy to do that. Like if you have an instance of something, you can't easily split it because all the other instances share this thing that is being shown. And also if you have meshes, even if they don't have instances, they might have additional shading data like baked textures in this example that makes it hard to split those things. So with that in mind, take this kind of content and spatial partitioning and do a little thought experiment and take this dumped down 2D, 1D, whatever example of Moana. So you have two base meshes, a rock and a mountain, the two green lines. And you have two types of trees, red and blue, and multiple instances of that. And let's do a spatial partitioning. So take something that's partitions into 3 ranks. I would claim that's actually pretty good partitioning. And you see right up front, it's very easy to trace array through that. Everything is easy. It's simple to do. All is good. Except if you look at what kind of meshes actually overlap each of these spatial domains, you'll see that every one of these ranks has 3 of the 4 meshes that it actually make up the entire scene. So if our idea of our goal was to reduce the number of meshes, the number of memory that each rank has, this was a total failure. It doesn't actually work that well. We wanted to have 1/3 of the meshes on each of these 3 ranks. What we end up is 3/4. So that was not very good. The second thing is, if you trace these rays through that I've shown here, these rays actually touch both rank 0 and rank 2, even though they're not even close to the geometry. And that means these rays have to be sent to these nodes, and that consumes bandwidth, and it's expensive. So it's not even good from a performance standpoint. So if spatial is bad, how would object space look? Now do something really dumb and take all of the red trees, put it on one rank, take the blue trees, put it on another rank, and take all the other geometry and put it on the 3rd rank. And then put some bounding boxes around it and do some magic, just hypothetically. The first things you realize is actually it's pretty good in terms of partitioning, because now every rank only has a very little amount of memory. So that is really good. But you have to somehow be able to traverse that. And that's not so easy. And in particular, if you just use these boxes for traversal, that would be horrible because every rank would have to go to every ray would have to go to every rank. But if you look at some of the papers and techniques that we built for BVH construction in ray tracing in the last few years, in particular spatial splits and rebraiding, the idea there was that if you have large unsplittable objects or instances, you can represent them often with smaller and tighter boxes if you use multiple boxes. So let's do the same thing here and represent each of the meshes with multiple smaller boxes and reach into the objects and put a single box around each instance. And suddenly this would look much, much, much better. We still have the benefits from the object space partitioning, but the ray, if we had a clever traversal algorithm, in this case would not have to move at all. All the work could be done on the right node. So that is basically what we want to be able to achieve. Now with that, the question is, how can we actually do that? The first insight that we had is that we have to think a little bit harder about how we actually want to represent remote context or a distributed scene. And we do that in our paper in the final version with what we call proxies. A proxy is a region of space, basically a 3D bounding box, that contains something. That something could be a part of a mesh, it could be an entire mesh, it could be 50 instances. It's something. And it also contains a list of nodes, typically one, but could be multiple if we replicate certain stuff, which we can, that own this content. So every other node, if it comes to this box, knows there's something on this other node that we have to ask this other node about. So that is the basic representation that we use. Most naively, think of looking at each instance, assigning each instance to exactly one rank, and put bounding boxes around that. So take this scene, for example, 3 different types of trees. We sort them once again by object type. So all of the red ones go one rank, the green ones another, and the blue ones another. Now we could put a bounding box around each one of these instances, world space, and that would be a valid set of proxies. That's the easiest way to think about that. But it doesn't have to be this way. We could also say, in some cases, we might to merge some of these instances into a single proxy, just to have less of these proxies around. Or we could do the opposite. If we have one that's just a giant box around this thing, like a base mesh, we can split it up into smaller ones and use multiple proxies to represent the same thing. And that is basically the power of this scheme, that if you know how to build it, and that of course is a challenge, then you can represent this really, really well. And the color of the boxes in this case basically encodes which nodes, which ranks have the data behind these boxes. Now, if you want to traverse that, the first idea that we had is we could just take all of these boxes. Every rank would get all of the boxes, even though they only have one content, and trace that through these boxes in a BVH-like way, maybe with a stack-free BVH traversal or something like that. So you would maybe first traverse the green one, then the red one, then the blue one, then the red one, etc. And that's kind of an obvious way to think of it, but there's lots of issues with that. It's for some reasons it's tricky to get it to work. You might have lots of proxies along the way, and you could actually, as in this case, you could go blue, red, blue, and that's just not reasonable. So we actually had to abandon that and had to find something better. So what we eventually end up doing is we have each ray track which nodes it's already been on, and there's 2 methods in the paper where we talk about how you can do that. And then when we build a BVH over these proxies and trace this ray into it, every time we trace that, we always find the first proxy that is on a node that we have not yet been on. So we basically disable all the nodes with any hit program that we've already been on and find the closest one we have not. So take this scene, for example, similar to the one before, with this kind of partitioning. This is the proxies that we would have in this case. Every node would have that. And now assume we're tracing a ray off the green node, a secondary ray. Maybe we shaded the green palm, and that was a shadow ray or a reflection ray. And that's the ray we want to trace. So the first thing we obviously want to do is trace the ray on that green node. It doesn't matter what the first proxy is. We want to do it on this node because it's already there. Why would we send it anywhere else? Then after that, we mark the ray as I've been on green, so basically disable the green boxes, traces into the proxies, and find the closest one. In this case, that's the blue one. It overlaps the same origin, and that's perfectly fine. It's the closest box, so we send to the blue node. The blue node intersects the blue geometry, and after that, marks the ray as having been on blue, traces into the proxies, sends to the red node finds a hit point, we shade the hit point, etc., etc., etc. Right? So very simple. It's actually a bad example in a sense, because in this case, the ray actually had to go through all of the ranks to finally find the hit point. But I think it's easy to see if you think a little bit about it. If the proxies are good, then in many cases, it doesn't. In many cases, the ray can very quickly narrow it down to 1 or 2 candidates that it has to traverse. And that's basically what we're after. So the rest of the paper, not of this talk, is about how you can put this entire idea into practice. We're talking about how you can do the actual scene partitioning, which is a super tricky problem. We're talking about how you can track previously visited nodes and how we build a full system with that. And again, I don't have time to talk about that, so read the paper. Just as a teaser of the results, again, full evaluations in the paper, maybe the most important thing is object space splits are way better for partitioning this kind of model data. You generally have much less data per node for a given number of splits that you have. And that means you can reach the same memory budget faster. And very often we can reach memory budgets that with spatial we just can't get at all, just because we have so much replication going on. It's also a way more general way of representing context, because think you could move things around and that's fine. The boxes already overlap. It doesn't matter if they overlap more. So that is an important thing. A second interesting result is that with a good partitioning and good proxies, you can actually be faster than spatial partitioning, because if the proxies are tight, then I have less forwarding, and that means I'm faster. Super important is the proxies that we use, they don't have to overlap. They can actually also represent classical spatial partition. So our method is not an either or, it's actually a superset. You can use existing spatial data, spatially partitioned data. It works just fine. We do that in several follow-up projects. And finally, it actually works. It works great. Here's 2 screenshots from rendering this thing on 4 nodes with a total of 8 GPUs. You wouldn't actually need so many nodes for the object space partitioning. We only need it for the spatial partitioning as a reference. And it works great. You can interactively run through there. It's both path tracing. There's no artifacts whatsoever. Noise, of course, a path tracer. But other than that, it just works great. So with that, I'm at the end of the time. There's a lot of details that I glossed over. I refer to the paper. I'm also fully admitting here there's several issues that are remaining here, in particular in the systems design, where you can try to get more performance. And maybe the biggest one is this problem of what is the best partitioning. We show there are some good ones, and they're better than spatial, but we don't yet have a solid handle on what is the best one. If you're looking for a challenging problem, let me know. Here is one. So that is also something that needs some further work. But other than that, we're really happy with the system that we have and with the results that we get, in particular, given that it's a relatively crappy home internet. And so we are very happy with the results that we have. And with that, I thank you for your attention, and I'm open for questions.
Thanks very much, Ingo. Really interesting questions. Or interesting paper. Now let's see who has questions. You can step to the mic with the button, the step to the mic button in the bottom right, and ask a question there, or you can type it. And if you type it, I'll read it off for Ingo. While other people are formulating their questions, I'll ask. So you get to the point where you've identified your proxies, you've built your proxies, and you know which proxies map to each rank.
Yep.
And then before you hand array off to that rank, in determining that the array needs to go to that rank for processing, do you put all of the proxies that pertain to that rank in a single subtree of a BBH? Is that how you know where it needs to go?
So right now, all of the proxies are replicated onto every rank. So every rank has all of the proxies, and they're all in one BBH. And each of those has basically a bit mask of all of the nodes that it is on, right? I said it's typically on one, but you could have things like the ground floor and replicate it if it's cheap. And then you trace array, and in the AnyHit program, you actually check these bit masks and say, hey, this thing is available on ranks 3 and 5, and I've actually already been on rank 3, so there's no reason for me to look at this geometry. I'll just kill that primitive and keep on going. And so the first proxy, the closest proxy that you hit that is not being rejected is one that you've definitely not been to yet and that you have to go to. That is the one that you get scheduled for.
Got it. Thank you. So here's a question in the chat. Is latency an issue as the array is sent over the network across nodes?
Yes, obviously. So first of all, we do not get like 100% GPU utilization. We are still very much bandwidth bound. There's things you could do to get performance up. You could have multiple different streams. You could have one set of streams that is shading and generating the new wavefront going out, while the other one is doing the MPI code to in and output. We're not doing that yet. There's actually a giant amount of systems work already in this. There would be like 2 papers just on that. So we haven't done that yet, but it would definitely be helpful to reduce this latency.
Thank you. Aaron, go ahead and ask your question live.
Hey, Ingo, really nice work. I was going to ask, is there anything you do differently for volume data, for example, as opposed to large mesh data in a system like this?
Yes and no. So we have a follow-up paper on that already. Well, it's not written yet, but we have several follow-up projects on that. One is on volume data, obviously. If your volume data, in most cases, if you have structured volume data, and most of the large data sets unfortunately are, then you don't actually need that much of it. You need just a spatial partitioning because the things don't overlap. And that's why I said I know it works for spatial partitioning, because we use that all the time for volume data. It gets a little bit more interesting once you have spatial, non-spatial partitions in the case of like fun 3D data with tetrahedral meshes, volumetric tetrahedral meshes, and they can overlap more. For that, we currently do some spatial partitioning, and that works just fine. We could also use this system to basically find the entry points to a mesh, then do the shading on that node, and then again use the system to find the next exit point. That is currently being worked on, but needs some re-engineering of the system. But I'm fairly sure it would work for that. And in fact, that's exactly one of the reasons why it was designed. And when I mentioned the generality of representing content, this kind of in situ application for visualization is exactly that. You do not want to repartition certain objects. You want to say, this node has this geometry, it overlaps other stuff, but shit happens. You have to be able to trace that. That's exactly what this is for.
Thanks. Next question is from Tammy Bubakur in the chat. You essentially defined proxies as bounding boxes. Would it make sense performance-wise to have more accurate proxies, geometrically speaking?
So yes and no. So the first thing is we have bounding boxes, but we have possibly multiple bounding boxes. So basically for large objects, think more of a voxelization. So we already get part of this benefit.
Okay, thank you. I'll give 10 seconds for any last questions.
And of course, if anybody has questions, send me an email.
Yeah. So thanks very much, Ingo and Steve. Great presentation, really illuminating ideas here. Let's thank our speaker one last time.